Alrighty guys, so we are just going to kind of speed through this first part so that I can talk math with you. So this unit is part 1 of unit 11. We're just going to cover solutions this week. So the first thing that we're going to talk about is what is a solution. So a solution is just a homogeneous mixture. So homogeneous means that it's all mixed the same. You can't tell the components apart. And it's important to know that a solution is not chemically changed. They're not chemically combined. There's not there's no reaction that has happened. These two things are just being completely intermixed with each other, okay? And they retain their original properties. So for example, if you have sugar water, so in sugar water, we're just gonna draw my little thing, okay? We add some sugar to the water. It mixes up and you can no longer tell that there's sugar in the water, right? Unless you taste it. When you taste it, it's still sweet. So that means that it is retaining the original property of the sugar and it's still liquidy, so you're still retaining the property of the water as well as other properties. So a solution is made up of two things. You have a solute and you have a solvent. In this situation, the solute would be the sugar. Sorry, I don't know why that happened. The solute would be the sugar. That's the thing that's being dissolved. So that's the stuff that we put in, okay? You put in the solute, okay? The liquid, it doesn't always have to be liquid. It can be it can be gas and stuff like that. But the liquid is going to be the solvent, the thing that is doing the dissolving. So in our situation, the solvent is going to be water. So our solvent is going to be our liquid or our gas or whatever the majority of the solution is. So like in our natural gas that we breathe, it's a high percentage of nitrogen. So really you could think of like the solvent of nitrogen since it's the higher percentage. But anyways, it's going to be the one that is the most abundant. So clearly in sugar water, the water is the most abundant, or it would just be wet sugar, okay? All right, so solutions. Water is our universal solvent because it has the ability to dissolve so many different substances. Remember that word aqueous or aqueous, however you want to say it. This is where water is the solvent, okay? Meaning that something is being dissolved in water. So for instance, like salt water is sodium chloride. This aqueous right here means that that is in water. So basically it's like you have this beaker and it looks clear, but really inside of there you have sodium ions and you have chlorine ions. So it's salt water and you have H2O, of course. That's what the big liquid is. Okay, solubility. So I know I'm going through these pretty fast, but I go in more detail in the actual PowerPoint, so you might want to listen to that first. Anyway, so solubility is kind of like our way of measuring how much and how well things dissolve. So solubility is the maximum amount of solute, okay? Solute is the stuff going in, dissolved in a particular solvent at a specific temperature. So it is dependent on if you change the solvent, then you obviously change the solubility, okay? Because some things are more or less soluble in certain solvents. And if you change the temperature, you also change the solubility. So it has to be a particular solvent at a particular temperature. So we have 3 different terms when it comes to solubility. We can be saturated. Saturated means that we are right there at the line. We have maxed out the amount of solute that can be dissolved. You can be unsaturated, which is like under the max, okay? So it would be less than. You can continue to add solute if it's unsaturated. And supersaturated is kind of like a weird, temporary, unstable condition. This is where the solute, there's more in there than you would think. So basically, if this is our line of saturation, this would be saturated, okay? This would be unsaturated because it's under it, and this would be super. All right, and we're going to look at that in a minute. So how do you make something super saturated? How do you get above this theoretical possibility? So you can just add a whole lot of stuff in, add a whole lot of solute. You can add more, so you would add like something, you would add the amount up here above the saturated. You're going to heat up the solution, and then you're going to slowly cool it back down. And the thought there is that that solute should like fall out of solution when you cool it back down, but it's temporary, and it's an unstable situation for the solution. The solute may not always fall out. It will eventually, and there's different ways that you can make the solute fall back out, but since this is temporary and unstable, so like there's certain ways you can put a stirring rod in, you can scratch the bottom of the glass and you'll see that you'll see that solute just like fall right on out. You could also, you could like put a piece in, so if it's like salt or something crystalline, you can put that in, and when you put that in again, you're going to see the solute fall out. Anyways, that's not as important as our solubility factors. So we are going to talk about factors that affect solubility, and we're also going to talk about the rate of dissolving. And they kind of seem the same, and you can get them intermixed, but why won't my screen slide? Okay, hold on. Okay. They have similar properties, but they're completely two different ideas. So when we're affecting the solubility, we're actually changing the amount that can be dissolved. Okay. So when it comes to solid substances, they have a higher solubility as the temperature increases. So for this one, I think about sugar water. So think about when you heat up water. More sugar can dissolve in hotter water, okay? It's the opposite for gases, so all gas solutes have a lower solubility as the temperature increases. Pressure can also affect solubility, but it only affects the gas ones, and so this one's actually, as one goes up, the other one goes up. So all gas solutes have a higher solubility as the pressure increases. So the main point is right here, most solid substances have higher solubility as the temperature increases. That's what matters to me. Okay, and we're going to prove that in a curve in our little graph here. So let's focus on this one first. So I want to point out multiple things to you. I want to point out the X and the Y axis. So if on the x-axis, you notice that the temperature is increasing as we go left to right, and on the y-axis, the solubility increases as we go down to up. So the solubility it's the grams of solvent per 100 grams of water, okay? And right here, this 100 grams of water is changing. So like, at this point, it would be at 10 degrees Celsius. Over here, it would be at 20 degrees Celsius. And so this temperature is changing. And so the other thing is changing is the number in front of grams. Okay. So I think in the PowerPoint, I picked this little NaNO3 sodium nitrate right there. And I tried to show you that as temperature increases, so does solubility. So at 10 degrees, let me use a different color. At 10 degrees, we'll follow this up right here. Our solubility is 80. So basically we're saying that we have 80 grams dissolving in 100 grams of water, okay? As we increase the temperature from 10 to 20, we get about, 88? So if you increase the temperature, the solubility also increased. So more solute, more of that sodium nitrate will dissolve in water at a higher temperature, okay? So right here for the solids, solutes, as temperature increased, so did the solubility. For the gas solutes, it's the complete opposite. So we'll look at carbon monoxide. So that's a terrible line. I can just erase that. Okay, so same idea, solubility versus temperature. So as the temperature increases, let's look at 10. At 10 degrees, you get what? Roughly 1.1 millimolarity? What is that? Yeah. And at 20 degrees, you get, this one was about 1.2, and this one is about 1. So this one over here, as temperature increased, your solubility decreased because you have a gas solid. Okay, so that is how your actual solubility. Remember, the solubility, this is how many grams will dissolve. Okay, the rate of dissolving, anything with rate is talking about the speed. So how fast will it dissolve? So just because it will dissolve faster does not mean you're changing the amount. So it should not be confused with how much. So temperature can also affect the rate. Now, temperature is the only one of these three that will also affect the solubility itself. So temperature is kind of like playing a double role here. It will increase the rate and it will also increase the solubility. You could also stir it. The stirring increases the interaction between the solute and the solvent, and therefore it will speed up the reaction. It will speed up the dissolving. And you can also powder it. So when I say powder it, it means like, am I putting a big chunk to where the only surface area is over here? Or am I putting a lot of little chunks? Okay, a lot of little chunks, you see how the surface area is on all of these little bitty pieces. So we're increasing the surface area here, so therefore we're going to increase the rate. So when we powder it, we're just talking about using smaller pieces. All right, liquid to liquid solutions, and then we'll finally get into concentration and the math, my favorite part. So liquid solutions, a lot of times this throws me back to organic, and we had what's called a separatory funnel. I'm a terrible drawer, goodness gracious. Okay, and so basically what the point was, I gotta redo that, that's annoying. So the point of this was, we had two liquids, okay? So we have like the sloshing liquid inside this funnel. This is our little like turn valve where it'll like drip out. Anyways, so you have solutions in here. If they are miscible, it all looks like there's just one big solution, okay? To where they are uniformly mixed together. When they are uniformly mixed together, that means that the two things in here are like. What I mean by that is we're now talking polarity. So it's either polar plus polar, or it's nonpolar plus nonpolar. Okay, that is when they are miscible. Okay, when we have our separatory funnel, give me a little break. Hold on, let me. Oh, why is it so awful? I know y'all are laughing at me. Stop. Okay, I'm gonna try real hard. That's a little better. And here's our stop thing. Okay, when it is immiscible, that means that we have two liquids that will not mix. So this is really what we like when we're talking about separatory funnels, because basically you get like a nonpolar and you get a polar. So you have a solution and then you'll have a line, and to where you can clearly see like one from the other. Okay, so this is immiscible. So this one right here, I don't even know if I spelled that right. So this one means that you do not have like with like, okay? So this means you have polar with nonpolar. You see how they're not the same over right here and how they were the same here every time they're the same? All right, so that's when you're mixing two liquids. It really comes in handy in lab. I love it when you get this scenario because you can separate the things. All right, so let's talk concentration. So I really like this picture because it kind of gives you a visual for like when you have less and when you have more. So when you have less, you're dilute, and when you have more, you're concentrated. So less meaning less solute and more meaning more solute. Okay, so here you get a pretty little picture, but of course everything is not colored and pretty and obvious. So like if I came up to you and I had a jug of concentrated sulfuric acid, like 12 molar, and I had another jug of 1 molar, so dilute sulfuric acid, you would not be able to tell just by looking at it which one is which. Okay, so it's not always this easy just to look at the colors, but this color gives you an idea that dilute means less and concentrated means more. Alrighty, so finally to the good stuff. So when we're talking molarity, molarity is our concentration unit. It's basically what we use when we're talking about concentration all the time. So molarity is symbolized by a capital M. We refer to things as like 12 molar or something like that. So it is the number of moles of solute dissolved in 1 liter of solution. Excuse me, I drank my coffee. All right, so we are going to say moles of moles of solute over liter solution. Okay, so this is, I'm going to change it to N over V, where N equals moles and V equals liter solution. It's important for you just to remember for your future chemistry needs that molarity is the total volume right here. It's the total volume. It's the whole solution, okay? Alrighty, so how do you make a certain solution? So really you're just gonna need a few things. You're gonna need your solute, you're gonna need your solvent, and you're gonna need some type of volumetric tool. Okay, in this situation, since it has this long neck on it, it is going to be a volumetric flask. So, do you see this little line right here? That line is zoomed in over here. That line tells us an exact measurement of volume. So, if I asked you to make a 0.5 molar solution and I gave you a 1 liter flask, if I put 1 liter on the bottom and say how many moles do I need for a 0.5 molar solution, obviously this has to be 0.5. So you need to measure out enough grams so that you can get half a mole of your solute. So that's half a mole. So what you do is you put this solute in your flask and then you fill the flask with water up to this line, or your solvent. In this case, it's water. You fill it up to that line and then you're just gonna stir it. There's different means of stirring, but that's basically what you do. All right, so let's get to the fun stuff. Calculations, yay. Okay, so this first one's pretty simple because it just says, what is the molarity? So our question is, I want pretty colors. Let's use these. Our question is question mark molarity. And we know from up here that molarity is N over V. So I know that molarity is the number of moles over the volume. And so what is the molarity of a solution that contains 0.25 moles, so N equals 0.25 moles of sodium chloride, in a 0.75 liter solution? So V equals 0.75 liter solution. So this is pretty simple. I know N, I can plug it in, and I know V, so I can plug that in. So I'm just going to do that. M equals 0.25 moles over 0.75 liter. When you do the math on that, you get 0.3 repeating molar or moles per liter, which is 0.3 molar NaCl. That's how we would write that. So it's pretty simple, right? I'm giving you the number of moles, I'm giving you the volume, you just plug it in, you solve for molarity. This next one, you actually are not solving for molarity, you're already given molarity. So this one's gonna look a little different. So this one says, what is the volume? Okay, so we're looking for volume and we know that M equals N over V. So we are looking for this variable. Let me change the color. We're looking for V, okay? And we know some things that we know. We know that M is equal to 1.08 moles per liter. And it says would contain 0.642 moles of potassium iodide. So we know that N is 0.642 moles Ki. All right, so since we're solving for V, let's rearrange this equation right here. So I have M equals N over V. I want to get V by itself. So the first step is to get it out of the denominator and multiply both sides by V, okay? That cancels the V and I get Vm equals N. Still, I'm still solving for V, so I want V by itself. So I still need to divide both sides by M to get V alone. That makes M cancel out here, and we get V equals N over M. That's a capital M. Okay, and that's a terrible V. Let me erase that. Okay, so now that we know how to solve it, now that we have our equation, we're just going to plug these values in. So we're going to say V equals 0.642 moles over 1.08 moles over liters. So mole and mole will cancel, and liter, since it's on the denominator of a denominator, will make it to the numerator. And our answer will be 0.59 liter solution. So that is how much volume that we need. Okay, let's do another one. Let's change our colors. All right, so this one says we're solving for grams, which is a little odd since this molarity, we've only been working with number of moles and volume. But we know how to go from grams to moles. That's our molar mass. Okay, so we're just going to put that there just so that we know. So we're solving for grams, and we know how to go from moles to grams. So we might have to do an extra step there at the end. So we want to know how many grams of calcium bromide are dissolved in 0.455 liters. So this is our V of a 0.39 molar calcium bromide solution. So M is equal to 0.39 moles per liter. I don't know why I wrote it like that. Okay, so again, we know M equals N over V, and we want to solve for G. Well, there is no G in this equation. There's no G, right? But there is an N. So we are actually going to solve for N first, and then once we solve for N, we can backtrack to G. So we need to rearrange this equation to get N by itself. So to do that, we want to multiply both sides by V, and that means V will cancel, and we get Vm equals N. And now, as you can see, N is by itself, so we can just plug in these values. Okay, that's a whole lot of errors. So let's solve. N equals, V is 0.455 liters, and M is 0.39 moles per liter. So that means liter cancels with liter, and we're left with moles. If you solve for that, you get 0.17745 moles. Okay, so I still have not gotten to my grams of calcium bromide. So I'm going to use this moles of calcium bromide to do a molar mass conversion. I'm going to do it over here. 0.17745 moles of calcium bromide. Since mole's on top, we're going to put mole on bottom. So 1 mole is equal to 200 grams of calcium bromide. Let me tell you where I got that 200. So for a molar mass, you want to take calcium bromide, separate them. You want to take how many you have. I have 1 calcium, 2 bromines. Multiply it by the mass off the periodic table, and this would give you a total of 200. Okay, so mole cancels, and we have gram of calcium bromide, which is what we're looking for. So then we just solve, and we get 35.49 grams calcium bromide. Let me tell you why this is like the most realistic problem that we've done. Because you don't just like measure out moles, because moles you have to count individual atoms, and that's like impossible for us. So like with the lab that we have, that's not, I mean, we're going to measure out grams, okay? Because that's like the most practical way to do this. So instead of just telling you that you need this amount of moles, if you told me to go get 0.17745 moles of calcium bromide, I would have to do this equation so that I can actually make it practical to a lab. Because as you saw in the lab that we did, we measure out grams. I can easily like pour a certain amount of grams out, okay? I can't pour a certain amount of moles out because I don't have a tool to measure that. So this is like the most practical problem that we've done with molarity. Okay, so the last little part of this unit, part 1, is molarity by dilution, which is really what we do a lot of in a lab, because you have these stock solutions that are highly concentrated, and you're not going to use that fully concentrated all the time. So you're all the time having to dilute a solution. So when you're diluting a solution, most of the time you're diluting it to a certain molarity and a certain volume. So normally this is going to be what you want. And you're starting with this other quantity, okay? That is what you are given. Okay, this is usually like our stock solution or our highly concentrated solution. And so this equation is one of my favorites. You'll hear it referred to as M1V1 equals M2V2, because you're taking the molarity of your original molarity times the original volume. Okay, this is your original. And you're trying to create a different molarity with a different volume. Okay, so this, again, this is what you want. So you're going to use that equation to do any type of dilution problem. And so here's an example down here. So it says, how do we make 5 liters of a 1.5 molar solution of KCl from a 12 molar stock solution? So basically what I'm saying is I have this big stock solution of 12 molar, and I want to know how many liters I want to take out of this 12 molar to make a 5 liter 1.5 molar solution. So essentially this is your M1V1 and this is your M2V2. Okay, so I don't know volume 1, so I am solving for V1. Okay, so I'm going to divide both sides by M1 to get V1 by itself, and that gives me V1 equals M2V2 over M1. So then you just plug in the numbers. Your M2 is going to be what you want, which is a 1.5 molar solution. Your V2 is 5 liters. That's how big you want your solution to be. That's how many liters you want. And it's all coming out of a 12 molar solution. So I need to know how much volume do I want to take from here to put it into there. And then the rest of that 5 liter will just be water. Okay. So when you do this math, so you say 1.5 times 5 divided by 12, you get 0.625 liters. So what that means is out of this big stock solution, I'm only going to measure 0.625 liters, okay? Or that's really 625 milliliters. That's how we look at it. Anyway, so that is your volume 1. That is what you solved for. So that's all I got for this solutions. I hope that you've watched it. I hope that you have learned. Please email me if you have any questions.